Welcome back to our ongoing exploration of differential geometry, the captivating realm where straight lines bend and surfaces curve in unexpected ways. In this second episode of our series, we will dive even deeper into the intricate world of curved spaces and surfaces. Building upon our foundation from the previous video, we will continue our journey by delving into the fascinating realm of spherical triangles. From their unique properties to their practical applications, we will uncover more about these geometric gems and their significance in differential geometry. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome part 2 of Learning Differential Geometry series. Now, before we go ahead into this video, first we will like to explore something which is called this. What is a spherical triangle? What are the features and what are its significance? But before we go into the spherical triangle, first we need to go back and understand this. Now, as we have said that the parallel axiom is equivalent to the facts that angles in a triangle sum up to pi. Now, if you can look into the typical Euclidean geometry, then you will see that the sum of the angles of a triangle is equal to 180 degrees. And this is what is typically called a parallel axiom. So I think that I really don't need to explain that. But yes, you can pause the video and read through it, which says that it forms two interior angles on the same side that are less than two right angles. Then the two lines, if they are extended indefinitely, then the angles that they form are less than two right angles. Now, taking ahead from that, what I was trying to tell is this one, that the parallel axiom is equivalent to the fact that angles in a triangle sum up to pi. So we are taking pi rad as 180 degrees, and it follows that both the spherical axiom and the hyperbolic axiom must lead into geometries in which the angles do not sum to pi. Right? It would not sum to pi, and in order to quantify this departure from Euclidean geometry, we will be introducing something which we are going to look into this video. So it says that in order to go into something else, we understood the parallel axiom, and then we see that it is not leading, that sum is not leading to pi. Now, if we consider the parallel axiom, then this is one of, I would say, the basic assumptions in Euclidean geometry. This is the one that is one of the basic assumptions in Euclidean geometry, and it states, just we have seen that given a line and a point on the line, there exists exactly one line that can be drawn parallel to a given point. Now, angles of a triangle, the sum of the angles of in any triangle, typically in Euclidean geometry, is always equal to pi radians or 180 degrees. Now, these two seemingly separate ideas are equivalent. This means that if you accept one as true, you can mathematically prove that the other to be true. If, for example, one is that if we assume the parallel axioms hold in your geometric system, you can prove that the angles in a triangle will sum up to pi radians. Conversely, if you can demonstrate that the angles of a triangle will always sum up to pi, then from here you can derive that the parallel axiom from that. So the equivalence is basically, a kind of a significance because it highlights the interconnectedness in the axioms of Euclidean geometry. Now, this understanding of the concept allows you to build upon and reach other important results. Now, note one point, that this equivalence of parallel axiom and this one only applies in Euclidean geometry. In other geometries like spherical geometry, parallel axiom might not hold true and the angles of a triangle might not add up to pi, which we are going to look up later. Now, in order to quantify this departure from Euclidean geometry, where the angles always hold this to be true, we introduce a new concept which is called angular excess, which is defined by the amount. I will show you the Greek sign. So this concept is something which is introduced to quantify how much of a triangle in a non-Euclidean geometry deviates from the Euclidean rule. And there is another concept which is called angular defect, And what this angular defect tells, it tells that the amount by which sum of angles in a triangle falls below pi radians in non-Euclidean geometry, particularly hyperbolic geometry. I will show you quick two examples. Say for example this one, the sum of the angles in a sphere I would say is always greater than pi. But in this kind of a surface, which I am going to explain to you later, the sum of the angles in a triangle is always less than the pi. Now this is what is called angular excess and another is angular defect. Remember, this defect is not in literary terms, but it's a mathematical term. Now why I am telling you angular excess and defect? Because this would lead to the next level of geometry, and we are going to see this angular defect, how it plays an important role. But before that, what I would like to show you is a quick example, a simple mathematical example. So imagine that you are working with a triangle on a sphere, something like this, and let us say that you are measuring this one, that is E equals to say for example sigma minus pi. Now this one is basically typically what is called is an angular excess. This actually the actual sum of the triangle, and pi is obviously the expected sum of angles in a Euclidean triangle. Now this notation in Greek etc., this might change. So if I take an example, say for example that the angles of a triangle, that the angles of this triangle, and find that they add up to 220 degrees, or say for example 3.83 radians or say. So we will take sigma as itself is the actual sum, so 3.83. We will take pi as 3.14, and once we deduct 3.83, we get 0.69 rad, and which is approximately 39.53 degrees. Now what it actually tells you is that the specific triangle on the sphere has an angular excess of so much radians compared to that of the Euclidean triangle. Now I would like to take a pause. I don't know whether you remember some of my lectures in general theory of relativity, where we were talking about parallel transport, and it shows how much a vector deviates from a normal Euclidean space to to a curved surface, basically spherical geometry. So you can take as an analogy that angular excess is something typically which would be something which is equivalent to parallel transport, just to make an intuitive understanding. But remember that this is not specifically right. So we get from this that means this specific triangle is this much excess compared to that of a Euclidean triangle. Now if I take this kind of a surface, okay, I will going to explain that, and imagine that the triangle, this is a hyperbolic saddle surface, so it's a hyperbolic geometry where the angles say for example add up to 2.61 or 2.62 radians. So we will take this one, and then we will take this one, and we will trying to find the defect. Defect means which is less. Obviously in the hyperbolic geometry it would be less. So it would be 3.14 minus 3.62, which would be approximately 0.52 or 0.53 radians, which will be 30.36 or 31 point something degrees. I've just made an approximation. What it tells, again, this signifies that the triangle has angles that add up to 0.53 radian less than what you would expect in a Euclidean geometry. Now typically you see this sets a stage that if you are trying to depart from Euclidean geometry, then how do we find the angular excess and the angular defect, thereby finding the amount of deviation in terms of angles which happens in the other geometry, typically from non-Euclidean geometry. So in this way also different types of covariant derivatives etc. are calculated in differential geometry and general relativity. So this becomes extremely important. Now we move on to the next part, where we will try to define something mathematically, which is the angular excess, which is defined by this Greek sign epsilon, and we can call it the angle of sum of a triangle, which is I would say use the equivalent sign, which is not obviously equal. And from here what we get is that this kind of a figure, if we try to get in, then if we try to get the the A, that is the area, this would lead to this. And if we are taking the radius, say for example you are taking the radius of the sphere to be r, then if we compare the triangle's angular excess with its area, and this area is basically only the small part which is in the northern hemisphere, which I just now highlighted, this one. This one is the fraction of the northern hemisphere. This would be theta by 2 pi, which would lead to this one, and this 2 pi r squared is basically we are taking the area of two circles in that case, and which would lead to this one. So epsilon would be equals to 1 upon r square followed by a. This curly a actually denotes basically the area. So we are actually trying to calculate in terms of mathematical equations, as I have earlier told, that this signs and formulas will be a little bit of change. Now this particular formula was actually invented, I would say in a part it was discovered in 1603 by English mathematician Thomas Hariot, who made this remarkable discovery. And remember, he was not only a mathematician, he was an astronomer, ethnographer and translator. And in 1603 he made this, and he claimed that this relationship actually holds for any triangle on the sphere. We will look into, because Thomas Hariot actually did not publish it, and we will look into the history later. So this is basically what he argued, that if you prolong the great circle, for example, that of a triangle which divides the surface of the sphere into 8 triangles. I've just shown the 4 triangles, which would be 1, 2, 3 and 4, right? Alpha, triangle alpha, triangle alpha, triangle beta and triangle gamma, each being paired with the congruent antipodal triangle. So from this is clear that if I take this kind of a figure, since the area of the sphere will be 4 pi r square, and we can deduce this one. So we will add the angle, then the angle alpha, then the angle beta, and then the angle gamma. Now from here what it becomes clear is that if I take this one, sorry, let me show you again the animation, that this triangle, the triangle and the triangle triangle alpha, the triangle and the triangle alpha, sub alpha, together they actually form a wedge whose area is a fraction again, which would be alpha by 2 pi area of the sphere. From here we get into this one, and similarly if we add the 2 of these, we will get 2 beta r squared and 2 gamma r squared. Remember, the capital R is basically the sphere of the radius sphere, and if we add these equations, I mean to say this one plus this one, then what we get is a big equation, this one. So you can just do the algebra and the mathematical calculation simply. Now again, taking forward with this equation, if we subtract this 2 pi r squared, which we just deduce this one from this one, this the big one which I just saw you few seconds earlier, we get something like this. And what we prove is this one. If you do the calculation and replace the r square epsilon with this one, what we see is that it actually proves this one. That means we have actually proved that through this calculation and adding the spheres, we will actually get this one. And this part, that is the epsilon, is equivalent to angles of the sum of a triangle. This is typically known as Girard's theorem. I'm sorry for my horrible French pronunciation. Now Girard's theorem is actually an earlier proof which was derived but was not published by the English mathematician Thomas Hariot. Albert Girard actually proved into this. And in the next part of the video, we are going to look into what is called the Girard's theorem, coming up into the next part of the video. Now Girard's theorem is again a very important element in terms of differential geometry, and here is Albert Girard. Remember that he was a French-born mathematician, studied at the University of Leiden, and he had earlier thoughts on the fundamental theory of algebra. I mean to say, what is the fundamental theory? It states that every non-constant single variable polynomial with complex coefficients has at least one complex root. And this includes polynomials with real coefficients, since every real number is a complex number with its imaginary part which is equal to 0. And these are few of his contributions in terms of mathematics. He was the first to use sine, cos, tan, etc. Now Girard's theorem actually showed, I mean to say, how the area of a spherical triangle depends upon the result. So here you see that the area, if I take T again, of a spherical triangle which contains the points as A, B, C, would be something which is equal to this one. So Girard's formula, Girard's theorem, anyway, so this is what he actually first found out to be. Now I want to give you a very intuitive understanding. Forget this mathematical part. I want to give you a fairly intuitive understanding of what is a Girard's theorem. Now I would like to imagine you this beach ball which has got these points as A, B and C, And what you are trying to do is draw a triangle, which I have tried to draw with this beach ball. So unlike a flat triangle, the angles of this beach ball triangle will always up to a little bit more than pi radians or 180 degrees. Because of what? Because of the curvature. Now, so what Girard's theorem actually tells you is this one. Girard's theorem actually tells you that it is a way to find out the area of the beach ball. So the more the curvy the triangle, that means the larger angles, that would be the bigger area. The bigger the beach ball, that means the radius is quite larger, the bigger the area of the sum of the triangle. The sum of the angles, for example, in this left hand side figure ABC will be more than 180 degrees, and this extra, I would say the extra angle sum tells you actually how much curvier, this is wrong English, how much curvier the triangle is, and the radius tells you how big the beach ball is. So combining all these factors, Girard's theorem actually helps you to calculate the area of this spherically, I would say, of this special curved triangle, which we will again explain what this triangle is all about. Now, Girard's theorem is not only true to pure mathematics or differential geometry, but it has got various applications. So here coming up few of the application of Girard's theorem. So what it says first is that this theorem is designed to for triangles drawn on curved surfaces of a sphere. It is obviously an exit from non-Euclidean geometry. The area and the angle relationship is actually a connection between the spherical triangle and the sum of the angles. The angular excess, which we just try to calculate, the angular excess and the angular defect, is basically the angles of a triangle which always sum up to pi radians, but as we have seen in sphere, due to this curvature, the area of the angles of a triangle add up to more than pi radians, and Girard's theorem actually includes these concepts of angular excess into the area formula. And finally, the formula considers the radius, the smaller or the bigger, whatever, of the sphere, as the sphere's radius increases, the area of the spherical triangle with the same angles will also increase proportionally. So this is something which is called the Girard's theorem, which is definitely a very important part in differential geometry. Now all these things, the Girard's theorem, the angular excess, are happening what is called this one. We are trying to find out what is the geometry on curved surfaces, and now we will explore what is called the geometry on curved surfaces coming up into the next part of the video. Now here is a sphere, right, and I have tried to give an analogy that you're tying up strings, knots, not typically knots but strings. So just as on the sphere we stretch a string over the surface and we try to find out the shortest or the straightest route between 2 points such as A and B, I have not mentioned those points, provided obviously that the string can slide around the surface easily and the tension in the string ensures that the resulting path is as short as possible. This is very important. This tension actually ensures what is called the resulting path. Obviously you understand that I am talking of geodesics, but these things will become slowly clear. Now these shortest paths on a curved surface are equivalent to the straight lines in the plane, and they will play a crucial role in our video, and these are called geodesics. So to use this new word, I mean to say, you all know what is a geodesic. We may say that the geodesics in the plane are straight lines and the geodesics on the sphere are basically what we call great circles. So geodesics, remember, there can be multiple geodesics, and this is a figure which I have taken from ResearchGate. So this shows that geodesics in the great circle, and there can be multiple geodesics where things become a little bit, I would say, more complicated. Now, if I take a kind of a weird figure like this, where we have already seen these 2 points A and B, straightforward, they are connected. But remember, you can see here these 2 points C and D. So for points C and D, we must imagine that the strings run over the inside of the surface. So try to imagine that the surface is made up of 2 thinly separated layers with the strings, I mean to say, they're strapped between them. I know it's a little bit odd, but I mean to say that is how it happens. So these are the 2 points C, A and B, and these are turning inside us. So this is how you imagine these things. Now here you see there are 2 points which are this and this, and we are trying to what I would say overlap these 2 surfaces. I'm trying to overlap these two surfaces, those who are made in the black dots, and here you can see those who are extended with white knots. Okay, so this is something which I'm trying to, I will just explain these things better. So just to give you a feel of this kind of a figure where we are trying to, imagine two thinly separated layers and the string traps, trapped between them. So again, let me show you this animation. This black dot, this is the line going, and this is, we are extending that black dot into the white one. Okay, so what next? Now you see again this figure. So this figure is actually, you can see the circumference of the circle, and I have drawn a circle right on the top. I'm trying to extend this one, so I've zoomed that. So this figure shows that how we may define, for example, this circle of radius r and at center C, that is the center C. And for that, what we are trying to do is that we are taking this string, this string. And we are assuming that the length of the string is r, and this string is again attached at this point C, that is the center of the circle, which has got a radius obviously small r. And keeping the string taut, you are trying to drag the other end round the surface here. Keeping the string taut, you're trying to drag it around the surface. But just as the angles of a triangle now in this non-Euclidean geometry no longer sum up to pi, so now the circumference of the circle will not equal to 2 pi r. In fact, another fact is that for this circle which I have just showing, the circumference is less than 2 pi r. The circumference is less than 2 pi r. So we try to define a string of length r, we try to put that string r, and let me show you again. So let us remove this. This is the string of length r. And to construct, we're trying to construct a geodesic circle. We are taking the piece of a string of length r, holding one at fixed point, this one C, keeping the string taut, dragging the other end around the surface here. But just as the angles of a triangle no longer sum up to this, so it will be no longer equal to 2 pi r, rather less than 2 pi r. Now you have also seen that we have tried to draw a triangle. And this is what is called the geodesic triangle. And the question is that, can we construct a geodesic triangle on this kind of a thinly strapped wire and this kind of a weird surface which has got a crooked body and which has got two layers? So we will look now into the next part of a video and try to understand very easily that what is a geodesic triangle. But before understanding that, I would like to show you that what it looks like. So it looks like this, this and this. Okay, so somehow it looks like this. So this is what is called a geodesic triangle. Now remember that we are not taking triangle in the Euclidean sense, because triangle means the angles which will be straight lines. These are not straight lines. So this is called a geodesic triangle. So what is a geodesic triangle? A geodesic triangle is a triangle formed by the shortest paths connecting these 2 points on a curved surface. So if I take this kind of a surface, which is again a zoomed version of the earlier one, the geodesic triangle will look like this. So I've just copied and pasted over it, right? Now geodesic triangle for different shapes will be different. For a cone, the geodesic triangle will be something like this. For a hyperbolic saddle shape, it will be something like this, and for a sphere it will be this. So the ultimate point is that unlike Euclidean triangles, where the angles always add up to 180 degrees, the sum of angles in the geodesic triangle can be more or less than I would say 180 degrees. Can be more or less than 180 degrees because it depends on what type of a manifold or surface that you are taking. Now we will look into this kind of a formation of geodesic triangle. So here are the 3 points we have taken it. Okay, and looking at this triangle, that is the triangle 1, you will straightforward find that it's clear that it sums up to more than pi. It sums up to more than pi. That means epsilon delta 1 will be greater than 0, obviously, like a triangle in a spherical geometry. On the other hand, if I take these 3 points, you can clearly see that the angles of the angles of this triangle, that is triangle 2, sum to less than pi. That means epsilon triangle 2 will be less than 0. And this opposite behavior is actually more, I would say, pronounced in the triangles in hyperbolic geometry. Now, if you construct a circle, I'm so sorry, I cannot construct that. If you construct a circle on a saddle-shaped, surface, then the circumference will be greater than 2 pi r. And you can do that. I have not been able to do so. You can do that and let me know in the comment box. Now, this concept of what we call geodesic, this concept which we are right now learning in terms of geodesic, is actually belong to what is called intrinsic and extrinsic geometry. And I'm coming up in the next part of the video what is called an intrinsic and extrinsic geometry. We will take a quick understanding because this concept is so central and important in differential geometry. What is an intrinsic and what is an extrinsic geometry? Now, the concept of this geodesics or this intrinsic geometry was first introduced by the Prince of Mathematics, Carl Friedrich Gauss. So, it is clear that intrinsic geometry is something which is unaltered when the surface is bent, as a piece of paper, etc. can be. That means the main focus is on the inherent property of the shape itself, independent of whatever it is positioned, wherever it is embedded. So here are a few of the diagrams which I have taken from the book Visual Differential Geometry by Tristan Needham, to be honest. And these shapes, I mean to say, you can think that if there is an ant-like creature within the surface, such changes are I would say utterly undetectable. So intrinsically these surfaces have undergone no change at all. So as long as the distance within the surfaces are not stretched in any way, there has been absolutely no change. This is what is called intrinsic geometry. Now, this is credited by Carl Friedrich Gauss. If we take the same things and if we take this part of the triangle, the left hand side, which is a triangle drawn on a piece of paper, then you can see that it forms basically 90, 30 and a 60-degree angles. We can tell it as pi by 2, pi by 6 and pi by 3. And of course, the epsilon triangle would be equal to 0. And clearly we can bend such a flat of piece of paper into either of the two extrinsically curved on the surfaces which is on the right. So what we see, intrinsically these surfaces have not gone any change. They are both flat and they retain their shapes. And most importantly is that they are identical as that if the intelligent ant is creeping down. So we can bend such a piece of paper in either way and the curved surfaces on the right. But however, what you can find out here is that intrinsically these surfaces have not gone a change at all, but extrinsically the geometry surface etc. has changed. Now if we can patch this we can take a patch. I'm just taking a patch of a surface that is intrinsically curved so that a triangle within it has I would say epsilon not equals to 0, then it too can generally be bent, I would say, somewhat without stretching or tearing it, and thereby we are altering its extrinsic geometry while leaving its intrinsic geometry unchanged. Again, I would like to repeat that if you're taking this epsilon not equals to 0, it too can generally be bent somehow without stretching or tearing it, thereby altering its extrinsic geometry while leaving the intrinsic geometry unaltered. Extrinsically it is altered but intrinsically not. I mean to say, you can just take a visual example that you take a ping pong ball and gently you need to cut that ping pong ball right from the middle and gently squeeze the rim in one of these hemisphere, distorting the circular rim into an oval, but not an oval lying in the single plane. So here comes few of the significant points of intrinsic and extrinsic geometry. As far as the definition is concerned, deals with properties independent of embedding. Consider properties dependent. Examples are curvature, lengths, angles, etc. Here it is shape, distance in higher dimension. Advantages, I would say, insight into intrinsic nature. It is very useful in mathematics, and the important features are its focus is on deformation, etc. And extrinsic would be understanding interaction, ambient space, practical, and concern the deformation, transformation, extrinsic curvature, etc. So that's all for today's video. I will be continuing with the third part, and so on. And this is the way I think is the best way to learn differential geometry. And I'm immensely thankful for you who are taking up time to watch this video. Please do subscribe and click on the bell icon and subscribe to my channel Physics for Students. You can always write to me on this channel, and you can subscribe to my other channel General Relativity Explained, where I'm putting up videos mostly related to Einstein's general theory of relativity. And you can follow me on my Facebook, LinkedIn, Instagram and Twitter account. Don't miss those upcoming podcasts which is coming up right tomorrow with none other than Professor Justin Clark Duan on a very demanding and an important subject called the philosophy of mathematics, starting 4 p.m. Indian Standard Time right on this channel Physics for Students. Thank you very much, and may the good Lord be with you.